Well, good evening, and my name is Curtis Brown, and I'm joined here by Steve Kokoska. Tom Dick will be joining us very shortly. In the chat box, here we go. Tom is joining us now. I wanted to just welcome you all to Monday Night Calculus. We're going to be talking about, what are we talking about tonight, Steve?
Differentiability.
Differentiability and local linearity. We're looking forward to that. Hopefully you guys can get started. If you have not already, go ahead and download the questions down below in the description. If you haven't gotten those already, welcome students. Also want to make sure that we welcome the students. Pop something in the chat. Let us know you're here. If you've got questions, always happy to answer those. Otherwise, I think, Steve, I'll let you go ahead and get us started.
All righty. Thank you very much, Curtis. Great to be with you and Tom once again. I think we have some very nice problems here tonight, and I would encourage participants to ask and answer questions. I've got a couple special ones for you too, Curtis, so I hope you're on your top of your game tonight.
Oh, man.
Yeah, here's a good one. I was just telling Tom before we came on, we write these, I write these questions almost a month or 2 months ahead of time, and I just saw a question very similar to this that came up on Facebook. I believe the claim was that this was from AP Classroom. This is not the one from AP Classroom, but it is very similar to the problem that was asked about. So let's take a look at this. It's a little different, and I really like this one. It says, suppose f is a differentiable function, and suppose we know that f of 3 is 7 and f prime of 3 is equal to 5. And we just want to determine whether each of the following statements is true or false. I'm going to try to give a reason for our answers. All right, so the very first statement we were given here, I believe in the question, was this one. The limit as x goes to 3 of f of x is equal to 7. Well, it turns out that this statement is true, and here's why. We know that f is a differentiable function, and so if f is differentiable, it must be continuous. That's one of the standard theorems that students learn in AP Calculus, and it has been tested in a variety of ways and frequently on the AP Calculus exam. So if f is differentiable, we know that it's continuous, and therefore, if we want to evaluate this limit, we can do so by direct substitution, and we know that f of 3 is equal to 7 from up here, and so son of a gun, that limit statement is true. All right, let me arrow up a little bit if I can. Hey, I might have the hang of this by now, I'm not sure. The limit as x goes to 3 of f of x minus f of 3 over x minus 3 is equal to 5. Well, this one turns out to be true also. And the way that we do this is, I think, a problem-solving technique, pattern recognition. We have to look at this expression here and recognize that that is in the form of what I would call, what many of us call the alternate definition of the derivative. Not necessarily the first one that we learn, but it is the alternate definition of the derivative of f at x equal to 3. So the definition of the derivative of f at 3 is simply this right here. And we're given up above that f prime of 3 is equal to 5. And so son of a gun, that limit has to be equal to 5. So that one's true also. Moving down the line here, the limit as as h goes to 0, or f of 3 plus h minus 7 over h is equal to 5. Again, this is another sort of very common, what's the right word here, form or expression that we see on the AP Calculus exam, generally on the multiple choice questions. But this is true also. And this comes from, we can show this by considering the definition of derivative of f at x equal to 3. Here's the definition of the derivative of f at 3. We know that f of 3 is equal to 7. That's given to us up above. We know that this is the definition of the derivative of f at 3. And we're given that f prime of 3 is equal to 5. And so son of a gun, That must be true also. Cool. Let's try another one. See if I got this. I'm going to try to arrow up just a little bit to give myself a little bit more room. Here we go. How about the limit as h goes to 0, this time from the right, of f of 3 plus h minus f of 3 divided by h? Well, this one is also true, and here's why. We know that f prime of 3 is equal to 7. We know that f is differentiable at x equal to 3, and therefore we know that this overall limit right here is the definition of the derivative of f at 3, which is given to us is equal to 5. So there's a couple of cool theorems, a couple of cool ideas coming in here. This is often the way that free response questions are framed or written, so that students have to bring in several ideas to answer a question. This overall limit exists. Therefore, the two one-sided limits must exist. And therefore, this limit as h goes to 0 from the right of that quotient must also be equal to 5. So that one's true also. Now again, I think to the real interesting one here, which is part E. And this one says the limit as x goes to 3 of f prime of x is equal to 5. Now you might just kind of quickly think that that's true, because it says up here in the given, if you look back a page, that f prime of 3 is equal to 5. And so you might think, well, okay, we'll just plug in 3 like we did for just f, and f prime of 3 is equal to 5. That must be true. But the problem is that we don't know that f prime is continuous. We know that f is differentiable. We don't know that it's twice differentiable. We don't know, therefore, that f prime is continuous. And therefore, we cannot use direct substitution. And therefore, we cannot assume that this limit is equal to 5. So there's a standard sort of counterexample for this one, and we won't go through this in gory detail, but I think Tom will have a nice graphical approach to this. Here's the standard example. Take a look at this function f that I've defined, and I'm sorry that I used the same label here, f, as the one in my problem, but here's a new function, f. It's defined to be x squared times the sine of 1 over x, where x is not 0. We can't plug in an x equal to 0 in that expression. And we'll let it be equal to 0 at 0. It turns out for this expression that the derivative at x equals 0 is defined. And it turns out that f prime of 0 is equal to 0. But if you take a look at the tangent lines as we approach 0, and if you take a look at that graph that I've drawn down below, there's a graph of x squared, sine of 1 over x. The tangent lines actually oscillate as this graph approaches 0. And they never really zero in, pardon me, the slope of those tangent lines, therefore, never really zero in on any one number. That means if we looked at the limit as x goes to 0 of f prime of x, it doesn't exist. Yet, the derivative at 0 is equal to 0. That's really weird. Tom, I'm going to let you try to show that visually, if you would. Can you try
I'll
that?
give it a shot. Hey, Steve, I
Okay.
do have a quick comment, and it just occurred to me just now. And so I
Okay.
apologize for not giving you any forewarning on this. Is
Okay.
I think I would quibble just a little bit with your answer on part E.
Okay.
And my quibble would be, rather than say I don't think we know whether it's true or false.
Well, that's right.
It's
That's
actually a
correct.
cannot be determined. We don't know whether
That's
this is
correct.
true or false. It could be true. It could be false.
Correct.
We just don't know. So,
We don't know. Yep.
but your
True.
point's well taken. It's one that it's definitely, we can't jump to thinking that it's true. That's definitely not the case. So, okay.
All right. I'll hand it over to technology.
All right. And I hope it will come up all right. Let's see. Whoops.
Well, it was looking good, Tom.
It was. Let me get another shot there.
Hey, how
Does
about
it
that?
look okay?
Yes, sir.
All right. So you can see this is fresh out of the thing. Let's see, y equals. So what I'd like to do is look at that really strange function you were looking at right at the end,
Please,
Steve. So
please.
this was actually a piecewise function, though the two pieces, it was one formula for all real numbers except zero, and
Hmm.
then it was defined to be zero at zero. So let's see if how we can do that. Let's pull up a math menu here. And let's see if we scroll down, what I'm looking for is that piecewise. There it is, piecewise. And we've just got two pieces here. So let me
Uh-huh.
ratchet that down to two. And okay, so one piece was this x squared times the
Whoops,
sine of 1
whoops.
over
Still
x.
up in the exponent there.
Oh, yes. Thank you, sir. That may be the most common typing mistake I make,
Oh, me too. Yeah,
is forgetting
yeah.
to come down out of the exponent.
Yep.
Yes. Thank you for catching that. Okay, and now this is where we can, in this piecewise template, this is where we can specify the part of the domain that this formula will be good for. So I'm going to go to the test menu. That's the shift of math. And let's see, let's look at conditions to see what we've got. I don't see a not equals, but maybe it's down there right at the very bottom. Ah, there it is. X not equal to zero.
Hmm.
Very nice. And then our second formula is it's just equal to zero at x equals zero. And I think I'll just, well, let me go ahead and do that test again. Conditions. And there's number 9. I'll just hit 9, x equal to 0. Very good. So we've got that function entered. And let me pull up just a window. Kind of my go-to window for most things is Zoom Decimal. And let's see what we get. And boy, this scaling, there's a little bit of a hiccup going on there near x equals 0. But it doesn't look too much like your graph, Steve. Not
No,
yet,
it
at
certainly
least. And I think that's because your scaling was of a different type.
Yes,
I'm
sir.
not sure your axes were marked, but let's see if we can get a little closer look. And I mean that literally. What I'd like to do is zoom in at the origin and see if we can pick up kind of what the behavior looks like there. So I'm just going to do a zoom in right at 0, 0. That's where we want to
Yeah,
be. So I'll hit enter again. All right. Now I'm seeing a little bit of,
oscillation there. Yeah.
yeah, a little bit, but it still looks pretty mild. So let's
Yes,
just hit
yes.
enter again. And that what's nice is once you've chosen that zoom in, if you just keep hitting enter, it will zoom in repeatedly. I'm a little bit suspicious here. Let's see what's my window look like here?
Oh, it
Well,
was.
it is zooming in equal
Yes, it
scale
is.
factors. Very interesting. So uh, it seems to be flattening out, doesn't it?
It looks that way, doesn't it?
Yeah. So let me do one more zoom in. Wow, wow. This zooming in with equal scale factors, it's looking very, very flat.
Yeah.
So that's interesting. But what we could do is change our window. Let's see, what if we were to go to the window and let's see, for Y min, Y max, what if we put in an extra 0 here, maybe an extra, yeah, let's try that, see what happens. I'm going to insert 0 and do that the same for the Y max. So what that did was effectively change my y scale to be 1/10 of what it was
Mhm.
while not changing the x scale. And let's go ahead and graph and see what that looks like. So now we're starting to pick up more of the oscillation, not so much right at the origin, but you can see that we're seeing more of this
Yeah.
oscillating behavior. And so we could, I think actually your a suggestion you made before we went on air, Steve, about maybe zooming in horizontally only in the y direction might be something which is actually different than what we do when we're zooming in for limits. There we zoom in horizontally. This would be zooming in vertically to see that wild oscillation.
Yeah.
It's very strange.
Yeah.
So if we wanted to zoom in just vertically, we could go to zoom and go to memory and go to set factors. And what I'm going to do is I'm going to set the x factor to 1
Mhm.
and the y factor, I'll go ahead and set it to 10. So this is going to be kind of interesting. We're going to be zooming in vertically.
Yeah.
Okay. And then I'll zoom in.
Hey, how do you like that?
Wow, now we're starting to see this wild oscillation. Oh my gosh, it's just crazy. So there's really some bizarre stuff happening, and the main point is the reason the derivative, the limit of the derivative doesn't exist is our tangent lines are going extremely sharp vertical, not vertical, but sharp sloping negative to sharp sloping positive, and bouncing between those two over and over again. So we're getting all kinds of different slope values. So there really is no limit to the slope values, even though the derivative itself does exist at x equals 0. Kind of a weird thing there.
Yeah.
Oh, in fact, now that I think of it, when we were just zooming in, the graph looked like it was approaching a horizontal line, which suggests that the derivative is 0 there.
Yeah.
So the local linearity is still coming into effect, but when
Yeah.
we zoom in vertically, we can see that there's still some wild stuff. So it's a very, very strange function.
Yeah.
And it's not a typical one. Once it basically is one of those that's used as a counterexample. Say, hey, you got to be careful making this assumption, like that statement on part E. So okay, I will
Very cool.
let me get back to the stop share and turn it back over to you, Steve.
Okay. Thanks, Tom. That was cool. All right. Let's take a look at number 2. I really like this problem, Curtis. It involves a function h here, which is defined in terms of a couple of absolute values. I believe that the two most important definitions in calculus, probably mathematics, are that of a function and of absolute value. To succeed in calculus and mathematics, boy, you have to know the definition of a function, you have to be able to use it, and you have to be able to use the definition of the absolute value. One of the things that my calculus teacher taught me in college was, when you're in a calculus class, whenever you have a problem that involves absolute value, one of the first things you have to do is work to get rid of the absolute value symbols. Somehow you have to rewrite a function, you have to rewrite the expression to get rid of the absolute value. So let's see if we can do that. I'm going to determine which values or all the values for which this function h is differentiable. And I'm going to do this one actually graphically. I'm not going to do this with limits or anything. I'm going to do this one graphically. Sometimes we're asked to solve a problem like that on the AP exam. So let's try, see if we can do this one. So here's how I attack this one, some problem solving strategy. I thought about the definition of absolute value, and I thought about, well, how do I evaluate those arguments? And I know that sort of the cutoff point in that first expression is x equal 1. To the left of 1, what's inside there will be negative. I have to do one thing with that expression to evaluate the absolute value. The other problem is at x equal minus 2. I know to the left of that, the expression in there is negative. To the right, it's positive. So this is really splitting up this function h into 3 pieces. at x equal -2 and at x equal 1. So let's see if I've got this right. If x is to the left of -2, strictly to the left of -2, what's inside here? This argument is negative. So how do you evaluate that absolute value? You take the opposite of the argument. What's inside here is negative. How do you evaluate that? You take the opposite of its argument. I'm going to simplify that a little. If I did that correctly, I have a -2x. Let's see, I've got a +1 and a -2, so -1. So that's what h of x looks like to the left of -2 without any absolute value symbols in it. Now, what happens when I cross over, thinking about a number line, I use that expression often. What happens when I cross over -2? Now, this expression inside, this argument inside, that absolute value becomes positive or 0. To evaluate it, it is just the argument. This expression here is still negative. To evaluate it, I take the opposite of that expression, and now a little bit of simplifying. And son of a gun, the x's cancel, and I'm left with just the constant 3. What happens when we cross over 1 on the number line? Well, both of these expressions are now positive. Their evaluation is just the argument. I simplify a little, and I've got a 2x. Let's see. I think that's a +1, isn't it? Yeah, I think that's a 2x + 1. So, okay, I graph this expression. There's a graph that I produced using Mathematica. Tom may produce this using technology. And we are asked, where is h differentiable? Well, it's differentiable everywhere here except where there are sharp corners. Where there are these sharp corners in that function, the curve is not smooth. We know that a differentiable function is smooth. And so just graphically, just visually, this function is differentiable everywhere except at -2 and 1. So I probably did way too much gory detail there, but I think I can see that visually. Let me arrow up just a little bit. I'm asked to write an explicit formula for h prime. Well, we know that there is no derivative for h at -2 and at 1, but I know the derivative on those 3 other intervals. I can see that by looking at, well, the expressions or the straight lines. And for example, the derivative in here between -2 and 1 is just 0 because, well, that's a horizontal line. And I'm asked to sketch the graphs of h and h prime on the same coordinate axes. Okay. The blue curve, if you can see the color, that's the graph of h. And if I've got all my open circles, if you can see this correctly, let's see, the derivative of h over here to the left of -2 is just -2. There it is. There's an open circle here. There's an open circle here, remember, because the derivative of h at -2 is not defined. The derivative of h in between here is 0. There's another open circle there. There's an open circle there. The derivative of h to the right of 1 is 2. Beautiful. That's kind of a nice problem. Tom, is there any technology you want to do with that?
Sure, Steve, if you can.
Okay, cool.
All right. Let's take a look. All right, I'll
there you go.
Screen again, and all right. So I think we're back on the, if you can see my screen, I'll just go back to y equals. And what I'd like to do is just enter that same function again that you had, Steve. So I'm going to up this, the weird one we had there. And I'll just enter it not in the piecewise way that you had resolved it to, but just in its original form with the 2 absolute values.
That'd be great.
I'll go to my math menu, and see, go to, is it num? There we go. Under num, we see absolute. ABS is a shorthand for absolute value. We'll hit enter there, but you notice that it comes up because I have the math print mode on. It actually comes up with nice absolute value symbols. So our first absolute value expression, I think it was x plus 1, or no, x minus 1, excuse me.
X minus
There
1,
we
yeah.
go, x minus 1. And then I'll right arrow to get outside that absolute value. And then we are going to add on another absolute value term. So I'll go back to the math menu again, over to num. There's that first one, absolute value. And then this one is the x plus 2 expression.
Beautiful.
There we go. And I know I had a really bizarre window, so I ran back to a window that looks okay. So let's go back to Zoom Decimal and take a look at what this looks like. Oh, there it is. It
Pretty good.
It's quite a bit like yours. It's a little bit out of view. We could change the window to see a little bit more of it, but this is okay. It just does extend linearly in those two directions like we had before. Now you had actually taken a look at the derivative. I'm wondering what it would look like if we took the numerical derivative of this.
I am too. Yeah, I have two questions. That's one of them. Yeah.
Yeah. So let's go to y equals, and let's go to y2 and actually use our numerical derivative. So I'll go to the math menu, and there it is down at number 8. I'll go ahead and I could hit the number 8, but I'll just go ahead and scroll down there. We see nderiv for numerical derivative. And then we get something that looks like our Leibniz derivative notation. We're taking the derivative with respect to x, and we're going to take that of y1. Okay, a shorthand to the y variables menu. We'll do the alpha of trace. There we go. There's y1. So I'll just hit enter. And then this will look a little bit funny, but what this is if you were using this on the calculator screen, here you would put your specific value of x that you would want to find the derivative at. Well, we're going to be graphing this as a function of x. So this will be lots of different x values across the screen. So I'm actually going to put x in there.
Before you leave that, Tom, I have a question.
Sure.
Yeah. So I know it would have probably too many x's in it, but can you say y1 of x if you wanted to?
Yeah, absolutely. There'd be no problem with doing that at all. And if you were doing something, it does recognize the y1 without putting it of x. But let's say you had a composition of functions. So if you had like y1 of x squared,
okay,
you would then definitely want to put in the parentheses there.
Okay, gotcha.
Okay, so basically either one is okay here, y1 of x or just the y1 like I put here. Okay. All right, well, let's take a look at this graph.
Wow.
So this looks a lot like the graph you had, Steve, but there is, if you look really close, there's something interesting happening at -2.
Yes.
And +1. Now that's those locations of those sharp corners on our original graph. As you rightly pointed out, because of those sharp corners, the derivative doesn't exist. In fact, if you were trying to do a limit of difference quotients, from one side, you would be getting the slope of this line. So for example, if you did difference quotients at x equal +1, from the left-hand side, your difference quotients would be giving you slopes of 2, while your left-hand difference quotients would be giving you slopes of 0. So you're getting two different limits. The general limit doesn't exist, so it's not differentiable. What the numerical derivative is doing is it's not doing an actual true derivative. It's actually taking the average of the left and right-hand difference quotients. Well, what's the average of 2 and 0? 1. And that's what's being plotted there. It's actually averaging the two.
Interesting.
I'll go ahead and do a trace in case people don't see it. let me go down to the red
I was
function,
just going to ask you to
actually
do that.
trace over to x equal 1, it's giving me a value 1. And that's not a true value for the derivative. So this is just a caution. Remember, when you're doing a numerical derivative, it's an approximation. And in fact, if you've got a function that has its graph has sharp corners like absolute value, here's a combination of absolute value functions. We've got a couple of sharp corners. It's going to actually read out a value that won't be a derivative value. What it is an average of two difference quotients. And so we're seeing that is positive 1 at x equal 1. If I was to jump over to negative 2, notice there it's averaging the left-hand difference quotients was giving me slopes of negative 2. The right-hand difference quotients are giving me slopes of 0. It actually averaged those two to come up with this. Well, if we're thinking of it as a true derivative, it's an erroneous value. We shouldn't get a value at all. Okay. But that's just a caution that if you use numerical derivative on a point where the function is not differentiable, it's going to be computing some average of difference quotients and coming up with a number that we can't accept as the. But everywhere else where it is, we do have a nice derivative value. It's giving us a very good approximation. In fact, it's right on the money here.
Tom, one other thing that, if it's possible for you to try, one thing that we teach our students is that if a function is differentiable at a specific value, when we zoom in on that value, it's locally linear. And
right.
So is it possible for you to zoom in near that point on the graph of f or h here, I guess? What is it, -2, 3?
Okay, so there's minus, let me go to the blue graph, the original graph.
Yeah, I'd like to zoom in there.
There's -2, 3. So you would like to zoom in on that point. Is that right?
To
Okay,
see,
let's do that.
does it become locally linear?
Yeah. So I'll go to zoom. Now I'll save myself some grief. I remember I was kind of playing around with the zoom factors. So let me go back to memory here and get those factors set back to what they are normally. And normally your X factor and Y factor are the same. I think the default is 4 for those. So let me make those equal so that when we zoom in, we'll be zooming in with equal scale factors in both directions.
Good.
Okay, so we've got that. And now I can hit zoom again and do a zoom in. And we should be right at that point.
Okay.
So at that point, -2, 3. And so let me zoom in at that point. Still looks like a sharp corner.
Indeed.
What you were referring to when you zoom in on a point where the function's differentiable, it should straighten out and look like a straight line. But here, you might be thinking I'm just playing around, but if I was to trace, if I'll just move 1 pixel over, you can see the increment is very, very small here.
Yeah.
I really am very close in on that point. And so if I keep zooming in, the sharp corner never disappears. And that's going to be true on like absolute value at x equals 0, the other sharp corner. So it goes both ways. In other words, if we zoom in over and over and over again, and the graph just does not straighten out, that is giving us evidence that's not differentiable there. So
That's
great.
Pretty cool.
Yeah.
Pretty cool.
All right. I'll let you bounce over to Curtis to see if anything's come up I should look at before I stop the share and turn it back over to Steve.
Nope, nothing in the chat tonight so far.
All right. So back to you, Steve.
Okay, very good. All right, Curtis, I tried to get all 8 of these graphs on the screen. I hope you can see all of them. And what I asked in this problem was to match the graph of the function, which are in A, B, C, and D, with the graph of its derivative down below. So let's see if we can reason some of these out, some good problem-solving skills here. Let's take a look at this function up here in A. I notice that as x increases from large negative towards 0, the function appears to be increasing, so that means its derivative must be positive. As I get to 0, it sure looks like I am at a local, maybe even an absolute maximum where the slope is 0, so the derivative ought to go through the origin. And then to the right of 0, that function is decreasing, and so the derivative must be negative. Are there any graphs down there in I through IV, 1 through 4, that satisfy that? And I think it's this one. I think it's graph 3. It's positive over here because the graph of f, the graph of the function, is increasing. It's 0 at 0, and then it's decreasing. And as x increases without bound, you can sense that the slope of those tangent lines are getting closer and closer to 0, as is the derivative. Cool. All right, let's see if we can do the next one over here on the right. So I'm looking at b. Here, this function seems to be, let's see, decreasing until about x equal -1. Then it's increasing until about x equal +1, and then decreasing again. So its derivative is going to have to be negative, positive, negative. Well, we don't have to look too far. I think that's number 2 down below. Let's see, the derivative is negative, the function is decreasing. It reaches a local minimum, maybe an absolute minimum there. It's 0 at -1. The function is increasing, the derivative is positive. The function is decreasing, the derivative is negative. Pretty cool. Very good. In C, on C up above, this function, let's see, is increasing to -1, decreasing to 1, and increasing. So let's see, we need a function that is positive, negative, positive. Well, okay, there's some nice reasoning here. That certainly looks like it might be a cubic polynomial. That's sort of the general shape. And so thinking about this a little bit, we know that its derivative would have to be a second degree or a quadratic. And that sure looks like I down here. It's positive where the function is increasing, negative where it's decreasing, and positive where it's increasing again. For that function over there in D, and to tie a little bit of this together with what we just did in the previous problem, let's see, this one is increasing, decreasing, and increasing, but it's got a couple of sharp corners or edges here. And so we know that the derivative at -1 and +1 doesn't exist. And we know that the 3 parts of this function are straight lines, constant slope, constant derivatives. The derivatives must be horizontal lines. So to the left of -1, there's the derivative, a horizontal line. The derivative does not exist, and positive, by the way, because the function is increasing. We have an open circle at -1. The function is decreasing, constant rate. Its derivative is a horizontal line segment. Open circle, increasing at a constant rate. So D goes with 4. Cool. I like that problem. A little different. I don't know if we see a matching problem like that on the exam, but I like that one. Tom, sorry. I apologize.
Oh, no problem. Steve, well, I definitely don't have a technology bit here, but I did have an observation. I don't know if this was something you had in mind or not, but it just occurred to me that your graph A,
Yes,
that looks like the graph of an even function.
it does indeed.
Yeah, because it looks symmetric with respect to the y-axis.
Correct.
And your other 3 functions, B, C, and D, they all look like odd functions.
They are indeed.
Meaning they're symmetric with respect to the origin if you rotated them 180 degrees around the origin. But your derivatives are exactly kind of the opposite of those even odd. So your derivative, number 3 was the derivative of the graph in A. That one is odd.
Uh-huh.
And the other 3 are even.
How about
I'm
that?
wondering, is that a general thing? That
I
might be an
wonder about
interesting
that.
challenge. If you have a differentiable function that's odd, does its derivative have to be even?
I
And
wonder
vice
if we,
versa.
I wonder if we could prove that.
Yeah.
Oh, you know what?
Something for people to chew on a little bit.
Curtis could prove that, I'm sure.
Give me a few minutes.
All right. Should I take a look at 4, Tom?
Sure,
Okay,
absolutely.
here we go. All right, so for this one, we're going to get an approximation and we're going to throw in an AP type question in here somewhere. Here's a function f defined to be the cube root of x, and we want to start out by finding an equation for the tangent line to the graph of f at the point where x is equal to 27. Well, okay, we're going to need the slope of the tangent line, so we need the first derivative of f. And let's see, to do that, I rewrote this a little bit. I wrote that as x to the 1/3. And I use the general power rule. Bring that power down 1/3 times x to the 1/3 minus 1 x to the minus 2/3. And then I rewrote it a little bit here, bringing that x to the minus 2/3 into the denominator. What's f prime of 27? Well, let's see. What's 27 raised to the 2/3 power? Well, the cube root of that is 3. I squared it. It's 9 times 3. That's 27. There's no other minus signs in here. So the slope of the tangent line at 27 is 1 divided by 27. How about that? So the equation or an equation of the tangent line is f prime at 27, 1 over 27 times x minus 27 plus f of 27. What's f of 27? Can I get that easily? Yeah, that's just the cube root of 27. So that's plus 3. And I'll leave it in that form. So there's an equation of the tangent line to the graph of f where x is equal to 27. Now, I guess A and B might be included as one sort of question on an AP FRQ, but we want to use this function L to approximate the cube root of 27.1. Let me see if I can arrow up a little bit. Here we go. And I'd like to know, is this approximation an overestimate or an underestimate, and justify your answer? Well, let's see. To find this approximation is pretty straightforward. I'm just going to plug in 27.1 into my function capital L. And okay, I had to go to technology to get that answer, but I carried it out to what, 6 decimal places there? I think it's 3.003704. Now, how do I decide whether or not that estimate is an overestimate or an underestimate? Well, in order to do that, we have to think a little bit about the concavity of this function. Now, how do we do that? Well, we have to take a look at the second derivative, and I did that, once again making use of the generalized power rule, or the general power rule, and a little bit of simplification. And here's an expression for the second derivative of f. Now, I'm going to call it an error, a common thing that some of us would do is just take one value like 27 or one value like 27.1 and plug it into that expression and use that and say, oh, well, the function is concave up or concave down at that point, and so now we can draw a conclusion. But you can't. What you really need to do is to determine concavity over an interval that contains that 27.1 and really ought to contain that 27 also. So I took a look at this interval 27 to 28. And on that interval, those values are positive. And so if I plug any of those values into this expression and take the cube root, well, that's positive. Raise it to the 5th power, that's positive. 2 and the 9 are positive, so that quotient is positive, but there's a negative sign out in front. And so that means over that interval, that second derivative is negative, and therefore the graph of f is concave down on that interval. So you can kind of picture this, and I apologize for not drawing a graph on this one, but that's a nice challenge for you to do with a little bit of technology. The graph is concave down on this interval, so that means my tangent line must be above the graph, and therefore my estimate is an overestimate. Cool. The one down below, I think, is a little different also. I can't recall seeing an AP exam question like this, but this says graph this function, which is the absolute value of L of x minus f of x. In words, what I'm really doing is I'm graphing sort of this, what I might call error function. And I'm going to graph it over this interval 26.5 to 27.5 and ask, well, over that interval, what's the range of possible errors? Well, that means, when I use the tangent line, that means what I want to do is try to find the largest value of that function y over that interval. Now, Tom will be able to do this much better with technology. But what I did is I drew a graph down there with Mathematica, and I think I did a little bit of solving. And I think I found that the range of possible errors is, of course, 0. And I think up to the largest value I could find was 0.00116. I probably should have rounded that to 3 decimal places, being AP Calculus, talking about AP Calc, but tried to be a little bit more accurate there. Tom, is there anything you can do with technology on this one?
Yeah, I think so. If I can
Okay,
give it
very
a
cool.
shot here.
Okay.
All right. So I'll share my screen again there. I think it's coming up okay. And I'll just go back to y equals and clear out these two functions. And just curious at looking at the functions you were just looking at, Steve. The first one was actually pretty simple, just the cube root of x. I'll write
Correct.
that as
Yep.
to the 1/3 power. Okay.
Yep. Good.
And then for y2, I'm going to actually put in not the derivative function or the numerical derivative for this, but actually the tangent line equation that you came up with.
Okay.
So I think that was, let's see, 1/27. I'm just going to write this kind of straight across here. 1/27 times x minus 27.
Yes, sir.
And then we had plus the cube root of 27, which turned out to be 3.
Good.
So that's the original function, and y2 is actually the equation for the tangent line at x equal 27, y equals 3. Okay. So, well, I know I should know better. I'll do a zoom decimal to start out with. And I see that, but we can see a nice cube root function is in blue. The tangent line function's in red. We see it, but we don't see where it touches. All right. That's because that's off screen. So we need to change our window here a bit. Let me go to my window. I kind of know in advance kind of where I need to be is I want to kind of center around positive 27.3. So I think my Y range is probably fine, but X min, why don't I go to, let's see, how about 20, and then X max, let's go to 33.2. That may sound weird, but what I was doing was taking the width of the screen and just kind of shifting it over. So I kind of did the arithmetic there, but I did want to kind of keep the screen square here. So let's enter that and graph it again. And oh, wow, even at regular scaling, these things look, I can see a little bit of difference. I can see patches of blue and stuff like that. If we were to actually zoom in on the 0.327. Let's see, let me do a trace. or excuse me, I had that backwards, 27 comma 3. That's really, I'm already at 26.6. Let's see, let me put in 27. There we are, 27.3. If I switch over to tracing on the tangent line, I get 27.3. But if I vary off of that off that point just a little bit, so I'm going to go just 1 pixel to the right. Okay, there's 27.1. This is my tangent line value, 3.0037. Actually, that's the one you wanted us to calculate, I think.
That is right. Yeah.
And if we compare that to the blue value, man, they're very, very close,
They
but
are
not
indeed.
quite. We see that the tangent line is starting to vary a little bit off of that.
Yeah.
And if I was to zoom in on that point 27 comma 3, I won't have to zoom in much. I'll zoom in at least once here. Wow, I occasionally see a little bit of blue there, maybe. I'm not sure. But if I zoom in again, these graphs are basically indistinguishable as you zoom in. And that's what we should expect if you zoom in on a differentiable function and its tangent line at a point. If you zoom in on that point with equal scale factors, it should be to where the two graphs cannot be distinguished visually. So, and then we can see that right here, which is very nice. That's all I've got on that one. I'll turn it back
If
to you.
it's possible, Tom, could you
Sure.
use a graph of that absolute value of the difference?
Oh, that's right. I didn't think, yeah, I should have thought of that. Yeah, so we've got Y1 and Y2 right there. So we could
Right.
make a Y3.
Yep.
Go to math. Let's see, absolute value. Let's see that. And let's see, did you have the tangent line? Well, I guess it doesn't really
Doesn't
matter.
matter.
We're doing
Yeah,
the
doesn't
absolute
matter.
value of the difference, right?
Yep.
But I'll go ahead and do a Y2.
Okay.
And this came up before, but I'm going to go ahead and put that of X
Okay.
minus Y1 of X. But I will point out that in this case, I could just refer to Y2 and Y1, and it would have understood I meant those as functions. And I think our window, actually, I'll tell you what I'll do. Let's me just go ahead and graph that in the window that we had before. But let me zoom out. How's about that? So I'll zoom. Oh, let's see. Yeah, let's try to zoom out, see what happens here. Oh, now we're starting to see that graph there.
Yeah, it's very close to 0 there. Yeah.
Yeah. Yeah, and in fact, oh yeah, I'm realizing the graph that you have on the on your notes, so your problem solutions there, you've got very, very different scalings in
Yes.
X and Y. So
Yeah.
let's go ahead and change that window to something similar. I think you've got like negative
Well,
26.5.
no, I went like 26 to 28.
She's not negative 26. Yes, right. So 26 to 28. All right.
Yeah,
Clear
I think
that. That makes sense. 26 to 28 in the X direction. That puts 27 right in the middle.
Yeah, and the Y direction was 0 because we have an absolute value up to try 0.0003.
Okay. I'm gonna just to get the x-axis, or yeah, the x-axis into the picture. I'll make this 0.0001, negative 0.0001.
Okay. Yep.
And make the y max 0.0003.
Okay.
That's just so we'll have the x-axis as kind of a reference there.
Yep,
okay,
gotcha.
Let's graph this and see what happens.
Hey,
now we get something that looks very similar to what you had.
Yep.
No.
So how do you can you on the graph screen, Tom, can you solve, for example, find where that curve is equal to, you can just get a value where it's 27.5 or where it's 26.5, right? You can just evaluate that.
Yeah, we just evaluate. In fact,
Right.
we just pull up the trace and if you're interested in the value at 27.5. Oh, wait a second. I'm on the blue function. That's our original function.
Yeah.
I need to do an up arrow to get to my Y3. Up arrow or down arrow would cycle through the three functions.
Yes.
So there's the one we want. Of course, the error is 0 right at 27.
Right.
If I typed in 27.5, we would see there's the error there. It's at
Yep.
1.13.
Yeah. So I
times
apologize.
10 to the minus fourth. Yeah.
I apologize, Tom. One other thing, if you hit second and calc just for a second.
Sure. Got a shot.
So could you try to use the maximum over an interval? Could you try option number 4 and say, ask the calculator to find the maximum value of this function from 26.5 to 27.5?
Let's give it a shot, see what
Okay.
happens. Okay. So I'll go down to maximum.
And just type
Left
in the left.
bound is we want 26.5.
Yep.
I'm just going to type it in. I could
Yeah.
scroll
Yeah.
over there. And the right bound is 27.5.
Please.
Now this is a very symmetric looking.
Yeah.
Well, it looks kind of symmetric. Maybe it's not really symmetric. Okay. And a guess, should I just guess 27?
And see what happens. Yeah.
Right in the middle, see what it
Yeah.
does. See if it flips a coin.
Hey, how about that?
Ah, so it went to the right.
Uh-huh.
Yeah, and I think this is probably not symmetric at all, is it? So
No, I don't think it is because of the cube
yeah,
root.
you're right. It looks very parabolic, doesn't it? That graph of the error looks very symmetric. When I say symmetric, I mean symmetric at that around that vertex point down here. But yeah, but it's not really. So the maximum was at the right end point of that interval, I think. Does that match up with what you were thinking?
Yes. Yeah.
Yeah. All right.
Very cool.
Good deal. All right. I'll turn off the share. And we're probably getting pretty close to the end here.
Yeah. Curtis, we've got a couple of other problems, but I just want to mention something about this one and we'll call it an evening.
Okay.
I like number 5. It's a nice word problem and it's very typical of part of a free response question that students might see. So I would ask, I think this is a good one to do tomorrow morning at 8 a.m. when you first come in. Pay careful attention in part A to what the units are. And I will mention that I've changed the wording in this just a little to make it clearer. What I really have is a rate function S. And so that sometimes makes identifying these units of S prime a little bit more difficult, trickier, challenging. That's the better word. So make sure that you can do part A. And the other thing that I wanted to mention in part B is this is an application of the mean value theorem. And there have been problems on the exam like this for the last 3 or 4 years in a row. And one thing that students are missing, and I don't know if this will change this year because we do have a new chief reader, but one thing that many students have been missing is this. If you're going to apply the mean value theorem, you must know that this function is differentiable and is also continuous. And we're given that the function up here is differentiable, but we're not told that it is continuous. So the students must tell us that. And they must say, because S is differentiable, therefore it is continuous. And believe it or not, if a student wrote something like that, S is differentiable and continuous, they did not earn the point. They would have to convey that it is continuous because it is differentiable, which brings us all the way back to the very first problem we did tonight. How about that? So there's another problem or two here, Curtis, and we'll post these answers, these solutions. Tomorrow, I'll get them to you. Terrific.
That sounds good. That sounds good. Well,
Great.
didn't have a whole lot going on in the chat tonight. That's okay. There's a lot of good information. So Teachers, if you've watched this all the way through, maybe on the rerun or the playback, you can certainly, I'll put my email in the chat, and I will look for your requests for credit, professional development hours. We can certainly get that to you. And otherwise, we will see you here in about 2 weeks on November 4th. Will be our second to last Monday night calculus of the fall. So be looking forward to that one. Same time, same place. And until then, enjoy. All right. Well,
Terrific.
I don't know. We had a lot of people hit the like button, but